Hello, I am Kobayashi from Sony. In today's video, we will look at the mechanism for training neural networks. Anyone interested in learning about the basic thinking behind neural networks and the methods of design is encouraged to watch the videos in the Introduction to Deep Learning playlist. The link has been included in the description below. First, let's briefly review what it means to train a neural network. For example, if I now wanted to use a neural network to build a classifier for handwritten digits, I would first need to prepare a dataset to train the neural network. I will explain this using the example of a dataset for training a handwritten digits classifier called MNIST. This MNIST dataset includes 60,000 28 by 28 pixel monochrome images for training and the desired classification results that identify the images as one of the digits from 0 through 9. Next, we design the neural network to train using this data. The number of input neurons is the size of the input data for training. In this case, the size is 28 by 28 pixels, so we know that there are 784 input neurons. In addition, we prepare the number of neurons for the number of responses we want as output. In this case, it is 10 neurons corresponding to the 10 types of digits 0 through 9. As I explained in the video Basics of Designing Neural Network, if you design the number of layers and number of neurons respectively from input to output, you can design a neural network for use in training to classify handwritten digits. Immediately after it is designed, the neural network is similar to the brain of a human infant. The parameters, weights W, the strengths of connections between neurons in this neural network are all initialized with random numbers. The process of training involves repeatedly updating the weight W that has been initialized by these random numbers. So, how is training actually conducted? First, we have this training data, the 60,000 images. We'll select some suitable images from them. Next, we input the selected images in the unoptimized neural network that we just prepared, the infant brain, then calculate this neural network from left to right. The weights W of these connections between neurons have all been initialized with random numbers at the first stage, so the results of inputting images and calculating from left to right are also nonsense. For example, let's say that we input the image for the digit 1 and begin calculating from left to right. This really is the image for the digit 1, so we want the result for 1 to be 1.0 or 1 with 1.0 probability. However, at first, an incorrect classification result is output, such as 0.3 and a probability of 30% for the digit 6. However, when the input image for the digit 1 is input, ground truth table indicating that it is the digit 1 is added at the same time. Even if an incorrect result is output at this point, we conduct the process of updating the connection weight W that have been initialized with random numbers at first, so that the probability that it is the digit 1 approaches 1.0 and that the probability of the number being a digit other than 1, for example, the incorrect probability of 6, 0.3 approaches 0. Next, if we bring a different image from the training data and calculate from left to right, there is again a very high probability that it will be incorrect at the first stage. The process of training then consists of repeatedly making small updates to the connection weight W to achieve the correct result. For example, in the case of the MNIST dataset, the neural network can be sufficiently optimized by conducting training with the 60,000 images, repeating it 10 times for a total of 600,000 images. This is an image of a neural network that has been optimized in this manner. If, for example, we input the digit 2, a completely new image that has not been used for training, from the left, then calculate from left to right, making the probability of the digit 2 1.0 and the probability of any other digit 0.0, the correct answer will be output. If we adjust the connection weight W that was initialized with random numbers at first, so that training data outputs correct answers, we can train the neural network in the classification problem. Next, I would like to explain how to update parameter W so that the desired output can be obtained from the input in a bit more detail. In neural network training, parameter W that has been initialized with random numbers is usually updated using the mini-batch gradient descent method. As for the operation of the mini-batch gradient descent method, the first step is to obtain multiple sets of data called mini-batches from the training data. For example, let's say that we obtain about 256 samples per batch. Next, we use these mini-batches to conduct forward calculation. We place the input data in the left side and calculate in order from left to right. This calculation is conducted in the process of actually inputting images and conducting classification. Next, we compare the output from the neural network with the actual correct answer. Then we calculate the loss, namely the amount of deviation between the neural network output and the actual correct answer, and the degree to which classification is incorrect. This is the second step. In the third step, we use the loss value we just obtained to calculate the gradient of the parameter. I will use this figure to explain what a parameter gradient is. The vertical axis in this figure is loss value E and indicates the loss value. It is the loss value obtained in the second step. The larger this value is, the more difference there will be between the output of a neural network with incorrect classification and the actual correct answer. On the other hand, if the output of the neural network perfectly matches the correct answer, the loss will be zero. Next, the horizontal axis indicates parameter weight W. The actual neural network contains tens of thousands, tens of millions of parameters W. Here, to make it easier to understand, we are using only one of these dimensions on the horizontal axis. This weight W is initialized at first with random numbers, so the initial values are determined randomly. Using this weight W, we insert the mini-batch data, then calculate from left to right, and the obtained loss, the degree to which classification is incorrect, will be the value indicated by the vertical axis. This means that this single point can be plotted by conducting the first and second steps. The process of training consists of some type of relationship in the background between E and W, with the weight W being updated until the point at which E is at its smallest. In reality, the blue line drawn behind this cannot be measured, so we use a gradient to update W to make the loss value smaller in order to optimize the current weight W so that the loss becomes smaller. So what is this gradient? It indicates the slope of the tangent in relation to the blue line at the point of the current W. This is an image of it. The slope of the tangent is obtained with the third step, backward calculation, when the differential from the W of E is obtained. Intuitively, you could say that the gradient of this parameter W indicates the direction W is moved to increase the value of E. For example, in the case of a positive gradient such as this one, the loss value increases when W increases. On the other hand, you can expect the loss value to decrease when the value of W is decreased. Finally, we use the gradient of parameter W obtained in the backward calculation to conduct update process. This update process is conducted using the gradient we just obtained to move the current weight W in the direction that reduces loss E the most. As for the actual formula, when the gradient of the current weight W is multiplied by a small value for eta, the learning rate, then subtracted, the weight W can be moved in a direction that decreases the value of E. Any suitable small value, such as 0.1 or 0.01, is used for the actual eta. In steps 1 through 4, data is acquired from the training data, forward calculation is conducted from left to right, and the loss, which indicates the degree to which calculation was incorrect, is calculated. In the third step, we calculate the gradient of the parameter based on the loss. In the fourth step, we can expect that E will gradually grow smaller when we repeatedly update weight W based on the gradient of the parameter. This weight W can be updated by conducting this process repeatedly so that ultimately E becomes smaller for the overall data. This is optimization of the neural network through the mini-batch gradient descent method. A variety of optimization methods that are somewhat improved versions of the mini-batch gradient descent method are in practical use, but the basic steps of obtaining the gradient and updating the weight W in that direction are the same in all of those methods as well. Neural networks make it possible to achieve an extremely high level of classification that exceeds human performance. I find it intriguing that, despite it being an extremely high-performance technology, it is optimized with very basic ideas. Going a bit deeper, I will explain the specific type of calculation that is conducted in the third step, calculating the gradient of the parameter. In the third step, we use a technique called backpropagation to calculate the gradient of the parameter. To make the explanation of backpropagation easier to understand, the simplest neural network is shown here. In this neural network, input value x does not have multiple dimensions like images, but is one-dimensional scalar. The correct label is t. The value that we want this neural network to output is t. Pairs of these x and t are input in large quantities as training data. Next, we designate y as the classification results output from the neural network. Adding bias terms to affine as y equals wx plus b, we can obtain y from x, which becomes the main body of the classifier. Using conventional statistics terminology, this is single regression. So the loss function is the square of E equals y minus t, or in other words, the square error. The obtained loss value is output here. I will now explain the backpropagation algorithm using this extremely simple example. In the first step, the x and y data pair are brought in. Then in the second step, forward calculation is conducted to calculate y from x up to loss function E. What we want to obtain here using the results up to the loss function E is the differential with respect to the W of loss E. Next, because it is necessary to update bias B through training, the two differentials with respect to the B of loss E are required for updating the affine parameter. Next, I will explain how to obtain this gradient. This is an extremely simple neural network that only uses affine and square error, but by combining these functions, a very complex computational graph is created. And it is necessary to update parameters in such a complex computational graph. With a neural network that makes it possible to combine functions in a variety of forms, how can we make it possible to obtain the gradient of this parameter? Calculating the gradient while going backward in order from output makes it possible to obtain the gradient of each parameter even in the most complex computational graph. This is an algorithm called backpropagation. You probably studied composite function differentials in your high school math class. You could say that this backpropagation is able to differentiate composite functions efficiently in computers. Next, we will look at the specific operation of backpropagation. Instead of obtaining the differential for the W of E right off, we first obtain the differential of the Y of E. This is square error. The square of E equals y minus t. It can be obtained by differentiating the function for y. Specifically, this 2 is brought to the front to make it 2 times y minus t. T is a value given as training data and y is obtained during the process of forward calculation, so this can be calculated as a specific value. Then, if we have the value resulting from differentiating this E with respect to y, we can easily obtain the differentials for W and B as well. Next, the gradient of W is obtained from the gradient for y. It can be broken down in this manner. Using a technique that is often used in the differentiation of composite functions, we divide the gradient of w into two parts, the gradient of y and the result of differentiating y for w. The result of differentiating this formula with respect to w will be necessary. We already got the gradient of y, and we need a derivative of this equation with w, which is x. Therefore, the gradient of w for this parameter can be found by multiplying the value of x in the input data. We obtain the gradient of b in the same manner. In the same way that we did it earlier, the gradient of b can be divided into two parts, the gradient of y and the result of differentiating this formula with respect to b. When we differentiate this formula with respect to b, there is no coefficient, so we obtain 1. This means that the gradient of y becomes the gradient of b without changing. We have now calculated the specific gradient values respectively for w and b that are included in this neural network, so if we update the parameter according to the obtained gradient, we can optimize the neural network by repeating this action. Calculating the gradient of the intermediate node while going backward in order from the loss makes it possible to obtain the differential of parameters for the entire network. I use the simplest single regression to make this explanation simple. Even in cases in which functions such as convolution, max pooling, and ReLU are connected, the differential of composite functions can be used in exactly the same manner to calculate the gradient of the node. By repeating this process, we can calculate the gradient for even the deepest neural network. In today's tutorial, I have explained the mechanism of neural network training. As you saw, the mechanism of neural network training is extremely simple, with the concept of differentiation being the only thing coming up as mathematics. There are a variety of techniques other than neural networks for machine learning, but the mechanism of neural networks is the easiest to understand of all of the techniques. When utilizing deep learning, an understanding of this type of mechanism is not necessarily required. However, I believe that a solid understanding would be helpful in identifying the causes when training does not go well in some manner, for example, or if you are thinking about the architecture of a new neural network. It is not a difficult mechanism by any means, so I hope that you will take this opportunity to gain an understanding of it.